Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will discuss paper 3 of semester 2. Code for this paper 3 is DSC 5B. And name of this paper 3 is Differential Equations. First topic is differential equations of first order and first degree. We discuss on this topic unit 1 differential equations of first order and first degree. A differential equation of the first order and first degree containing two variables x and y is of the form m dx plus n dy equal to 0, where m and n are functions of x and y. In this topic, we consider first method, that is exact differential equation. How to solve this equation m dx plus n dy equal to 0 by exact differential equation method. Let us consider first the definition of exact differential equation. A differential equation which has been obtained from its primitive by differentiation only without any operation of elimination or reduction is said to be exact differential equation. That means a differential equation which is obtained from its primitive by differentiation only without any operation of elimination or reduction. This equation is known as exact differential equation. For example, a differential equation y dx plus x dy equal to 0 is exact since it can be obtained or it can be derived from its primitive xy equal to c by direct differentiation. That means if we take differentiation of d of xy, that is d of xy equal to x dy plus y dx and equal to derivative of c is 0. That means m dx plus n dy, that is y dx plus x dy equal to 0. This is equation is obtained from its primitive xy equal to c by direct differentiation. Hence, this is an exact differential equation by definition. That is y dx plus x dy equal to 0 is exact differential equation since it is obtained from its primitive xy equal to c by direct differentiation. Now we consider partial derivatives. Let z equal to f of xy be any function of variables x and y, then del by z by del by x equal to fx is partial derivative of z with respect to x. That is derivative of z with respect to x keeping y as constant. That is when y is constant, derivative of z with respect to x is denoted as del by z by del by x equal to fx. Here y is constant, derivative is with respect to x. Similarly, del by z by del by y equal to fy equal to derivative of z with respect to y keeping x as constant. We can write dz equal to del by z by del by x dx plus del by z by del by y dy. Now, del by del x of del z by del y equal to del 2z by del x del y, and del by del y of del z by del x equal to del 2z by del y del x. Always del 2z by del x del y equal to del 2z by del y del x. Now we have to prove one theorem, and statement of this theorem is the necessary and sufficient condition for the differential equation m dx plus n dy equal to 0 to be exact is that del by m by del by y equal to del by n by del by x. That is one objective question one can be asked, that is the necessary and sufficient condition for the differential equation m dx plus n dy equal to 0 is dash dash, that is del by m by del by y equal to del by n by del by x. Let us consider the proof of this theorem. First consider the necessary part. That means assume that m dx plus n dy equal to 0 is exact differential equation, and we have to prove that del by m by del by y equal to del by n by del by x. Thus we have assumed here that m dx plus n dy equal to 0 is exact differential equation. Hence, by definition of exact differential equation, this equation must be obtained from its primitive u is function of xy, u of xy equal to c, such that du equal to derivative with respect to x and derivative with respect to y, that is del by u by del by x dx plus del by u by del by y dy equal to 0. Hence, m dx plus n dy equal to del by u by del by x dx plus del by u by del by y dy. By equating the coefficients of dx, we get, by equating the coefficient of dx, we get m equal to del by u by del by x and n equal to del by u by del by y. By equating the coefficients of dx and dy on LHS and RHS, we get m equal to del by u by del by x and n equal to del by u by del by y. Now we take the derivative of m with respect to y, so that we get del by m by del by y equal to del by del by y of del by u by del by x, which is equal to del by 2u by del by y del by x, and del by n by del by x equal to del by del by x of del by u by del by y equal to del by 2u by del by x del by y. But we know that in general del by 2u by del by y del by x equal to del by 2u by del by x del by y. That is, we have considered these terms are always equal. That is, in general these terms are equal, so that we get, since these terms are in general equal, we get del by m by del by y equal to del by n by del by x. That means we have to prove this necessary condition, that is, when m dx plus n dy equal to 0 is exact differential equation, then the necessary condition for the equation m dx plus n dy equal to 0 to be exact is del by m by del by y equal to del by n by del by x. This term will be asked for objective, so that make bracket here. Now we consider the proof of sufficient part. In this part, we assume that del by m by del by y equal to del by n by del by x, and we have to prove that m dx plus n dy equal to 0 is an exact differential equation. Here we assume that integration of m dx equal to u. So that del by u by del by x, taking derivative of both sides, we get del by u by del by x equal to, taking derivative and integration are inverse process, so that they cancels with each other and only m remains. So that m equal to del by u by del by x. Now we take derivative of this term, derivative of both sides of this del by u by del by x equal to m with respect to y. We take partial derivative of this term m equal to del by u by del by x with respect to y. So that we get del by del by y of del by u by del by x, which is equal to del by 2u by del by y del by x equal to del by m by del by y. But we have seen that in general del by 2u by del by y del by x equal to del by 2u by del by x del by y. So that we get del by 2u by del by y del by x equal to del by n by del by x, since we have assumed that del by m by del by y equal to del by n by del by x. So that we take here del by n by del by x, and we replace this del by 2u by del by y del by x as del by 2u by del by x del by y, since in general they are equal. So that this is equal to del by n by del by x equal to del by 2u by del by x del by y, which is equal to del by y del by x of del by u by del by y. Integrating both sides with respect to x, treating y as constant, we get in taking integration, derivative and integration cancels, only n remains, equal to del by u by del by y plus constant of integration with respect to y, that is phi dash y. Hence, here we get m equal to del by u by del by x and n equal to del by u by del by y plus phi dash y. So that m dx plus n dy equal to del by u by del by x dx plus n is in bracket del by u by del by y plus phi dash y bracket complete dy, which is equal to del by u by del by x dx plus del by u by del by y dy plus bracket complete plus phi dash y dy, which is equal to, denote this bracket as du, since here derivative of u with respect to x and y is del by u by del by x dx plus del by u by del by y dy. So that we denote this bracket as du plus phi dash y dy. This can be represented as derivative of u plus phi of y, that is d into bracket u plus phi of y bracket complete. That means by taking simply the derivative of u plus phi of y, we get the term as del by u by del by x dx plus del by u by del by y dy plus phi dash y dy, which is equal to m dx plus n dy. That means the equation m dx plus n dy is obtained from its primitive u plus phi of y by differentiation only. So that this equation m dx plus n dy is an exact differential equation, since it is obtained from its primitive by differentiation only. Thus we get m dx plus n dy equal to 0 is an exact differential equation. Thus we have proved the sufficient part. That means we have assumed in this sufficient part we have assumed that del by m by del by y equal to del by n by del by x, and we have proved that m dx plus n dy equal to 0 is an exact differential equation. Thus in this theorem we have proved that the necessary and sufficient condition for m dx plus n dy equal to 0 is del by m by del by y equal to del by m by del by x. In this proof of the theorem, we proved the first part, that is necessary part, and second part is sufficient